Thanks, Ashley. Good afternoon from LI-COR Biosciences here in Lincoln, Nebraska. It's nice to see so many people have joined the webinar today. As Ashley mentioned, today we're going to talk about the LI-7200 CO2 H2O gas analyzer. We'll begin by going through some key features and advantages of the instrument. Then we'll show some data from field experiments. We'll show data that we collected to validate the details of the instrument, and we'll also show flux data that was calculated from the instrument and how it compares to flux data collected with other analyzers. We'll talk about instrument configurations and the operation of the instrument in the field, and we'll go through some questions and answers as well. If you missed the previous webinar, you can go to our website at www.licor.com and find that, and it's available for you to download and view at your convenience. Last time we did talk about open path gas analyzers like the LI-7200, and we talked about the excellent frequency response that they provide, long-term stability, their low sensitivity to contamination, and the fact that you can operate them with no pumps, which means that they have very low power requirements. And the long-term stability gives you really an opportunity to work without having to perform frequent calibrations. There's also a lot of benefits to using closed path analyzers in the field as well. They do give you much better data collection during precipitation and condensation events, and they'll allow for remote automated calibration if you'd like to set up a system that can check certified gases occasionally to make sure the instrument is performing properly. They also have a stable cell temperature. But today we're going to talk about a new kind of gas analyzer, the enclosed CO2 H2O analyzer, the LI-7200, that kind of takes items from both an open path and a closed path and brings them together. And before we do that, we've got a quick poll that we'd like to take just to see what kind of audience we're dealing with today. So we've got a question here. Do you currently operate eddy-covariance towers with open path or closed path CO2 analyzers? And your options are open path, closed path. I have some sites that use both if you operate multiple towers, or neither. I don't currently operate CO2 flux sites. So please go ahead and enter in your response there. We'll wait just a moment for that, and then we'll continue on. Okay, great. Well, thanks everybody for going ahead and giving us those answers. It looks like we've got quite a variety of responses, which we would expect. A lot of people using both open path and closed path instruments, so that's good to know. And like I said, we'd kind of expect that because there are benefits to both types of instruments depending on your field site and the kind of data you're trying to collect. As we move forward here, we'll talk more about, again, the new LI-7200 enclosed CO2 H2O analyzer. And the design of the 7200 allows it to operate really well in all kinds of different environmental conditions. It'll operate well when it's extremely cold or extremely hot, when it's very humid or very dry. Even in dusty conditions, the instrument really performs quite well. We'll be focusing a lot of our attention today on making eddy covariance measurements, but the LI-7200 can be used for all kinds of different measurements. You can use it for, storage measurements, profiles, gradients, relaxed eddy accumulation, canopy chambers or soil chambers, or any variety of different things. And you can also implement 7200s on ships or airplanes if you need to make mobile measurements. So there's a lot of flexibility in the instrument, and we'll talk a little bit more about that as well. I'd like to start by explaining what we mean by enclosed analyzer. The LI-7200 is what we call a compact enclosed gas analyzer, and it's really been based on the LI-7500 platform. We essentially designed this instrument to enclose the 7500's optical path, and that allows us to build on the benefits of the 7500, but also incorporate closed path benefits as well. So we still have high speed and precision that you're used to from LI-COR gas analyzers, and now we've also got the nice weatherized design, low power consumption, and high long-term stability, high-quality H2O fluxes that you're used to from the 7500 platform. And with this new enclosed approach, we can now combine these benefits along with great data collection during precipitation or condensation events, and the ability to check instrument calibration automatically and remotely. So we've really been able to combine benefits from both types of instruments. Just a couple of highlights for this enclosed analyzer approach are that the entire system, including the gas analyzer, airflow through the analyzer, and ability to log data, can operate with about 27 watts of power nominally. That's new and exciting for this market because in the past, to get a really low power gas analyzer, you had to go with an open path. And with the open path, you also have to deal with some additional data loss in bad weather. So now having this enclosed instrument that can not only make the measurement but also flow air through the instrument and log the data for 27 watts of power is a significant advantage. Just for a quick comparison, one incandescent household light bulb runs on 60 watts of power. And this entire eddy-covariance system now can run for about 27. So there's a significant low power advantage to using this new enclosed analyzer. Something else that's important about the 7200 is that because it's weatherized and it can be placed at the top of the tower near the sonic anemometer, you can use a short intake tube. Dave Johnson is going to discuss the benefits of that short intake tube in just a minute, but I just wanted to mention it here because it is important, because we want to be able to get the analyzer very close to the sonic anemometer but not influence the turbulent air structures that we're trying to measure. And the 7200 really allows for that in a new way. This enclosed instrument also has high-speed temperature and pressure measurements inside the cell, and Dave will speak to that in addition here in just a minute, but this is the first analyzer that's really been able to make really high-speed temperature and pressure measurements inside the optical cell at the same time as the gas measurement, so that provides some additional advantages. And now I'm going to go ahead and turn things over to Dave Johnson. He's the technical support manager for LI-COR, and he's got a lot of experience working in the field with our gas analyzers. He's going to go ahead and tell you more about some of the key details and features of the new 7200. Dave?
All right, thanks a lot, Bill. And I'd also like to thank everyone for attending the webinar, taking the time out of their day to find out a little bit more about our instruments and the science we've been doing here at LI-COR. As Bill mentioned, I wanted to, start off talking about the intake tubes. We need to know how to get the sample into the cell without attenuating the fluxes that we want to measure. Now, with open path instruments like the 7500, this usually isn't an issue. However, with traditional closed path instruments and some of the new ones that are out there, it's difficult to get that airstream from the sonic down to the gas analyzer, which is usually at the base of the tower in an enclosure. And this can require several meters of tubing, and those long lengths of tubing can often significantly attenuate the signal you're trying to measure. So because this new enclosed 7200 analyzer can be mounted at the top of the tower near the anemometer, we only need to have a short intake tube. So LI-COR is providing, with the 7200 package, a 1 meter intake tube. This has a 3/8 inch inner diameter. The tube is insulated, and it's also flexible, so you can bend it and position it to where you want to take your sample from. The short intake tubing can attenuate or dampen temperature fluctuations.
Dave, before you move on, I'm going to take the chance here to ask a couple of questions that are coming in from the audience. I have Mike who's asking, why is the optimum intake tube length between a 0.5 meter and 1 meter?
That's a very good question. For eddy-covariance measurements, it's best to attenuate temperature fluxes. However, you do not want to attenuate the water fluxes. These are the real measurements that we're trying to capture. So there's been several research projects, papers, such as the one by Clement et al. That's listed here on the slide. And what they found out is if the tube is too short, the temperatures will not attenuate. However, if the tube is too long, then the H2O fluxes will attenuate. And so this can happen with tubes that are a 1+ meter, where you start to see H2O fluxes being lost, and you can even see CO2 fluxes being lost if the tubing is up over 10 meters. So that's why it's important to find a middle ground here that is optimal for both. This 1 meter length can get you 95 to 99% temperature attenuations and still have minimal H2O and CO2 attenuation. Coming back to the slide here, the other point I wanted to make is that intake tubes can create a resistance to mass flow through the system. So the longer the tube you have, the greater the resistance is. This results in needing a larger pump, for example, to try and pull that air through the system. And of course, if you have a larger pump, you're going to require more power for your site. So having the short intake tubes is a good solution. Okay, so now we're going to look at some of the key features of the 7200, and one of those is having fast temperature measurements and fast pressure measurements inside the cell. So these are new and unique features that are not seen in other closed path analyzers. They make very fast measurements in the optical path, which is at the point of the measurement. So we have two temperature sensors, one on the inlet and one on the outlet, that are measuring at a rate of 20 Hertz. Similarly, we have a differential pressure sensor that is also measuring at 20 Hertz. So you might be asking, why are these important features? What are the benefits of having this? Well, first, it allows you to capture some of the variables for the WPL term. I'll talk a little bit more on this later in the presentation. Some of these variables are necessary for applying to the WPL term. Secondly, it allows for the conversion of number density, which is in milligrams per meter cubed, into molar fraction if you wanted to have micromoles per mole or even ppm.
Dave, I'm going to stop you again here. We have a question from Pam, and she's asking, can you output real time on the fly dry mole fraction?
That's another great question. We're actually looking into this. The 7200 is capable of fast output of mixing ratios, and they can be corrected for dilution and expansion using the instantaneous water, temperature, and the pressure measurements. So this can eliminate the need for applying the WPL terms. Again, I'm going to talk a little bit more about WPL in a couple slides here. However, to date, we haven't really been able to field test this. Some of the current issues relate to the timing synchronization for the temperature, the pressure, the CO2, the water, and the flow rates. But we are in the process of determining if this can be done in real time, and we're really excited about the prospects. So now here's a picture of the 7200 head. At the top, we have a couple thumb screws. This allows you to quickly open and access the 7200 head without having any tools. Next, we have the removable cell. This is the part that you can pull out and easily clean if you need to. There's a coupled metal body. This helps keep the temperature in the cell stable and the same throughout. Then we have the inlet and outlet ports. The inlet, of course, is where we attach the intake tube to pull the air into the analyzer, and the cell outlet can connect to the 7200-101, which is a flow module, or some other pump. And then, of course, there's a cable for capturing the fast temperature and pressure measurements.
Dave, I have another question for you, this time from Martin, and he's asking, how often do you need to maintain and clean the instrument?
Okay, Martin. The optics of this analyzer have a very low sensitivity to contamination, especially if you're to compare it to other closed path laser-based platforms. The 7200 is like the 7500. It has an automatic gain control feedback loop, and this allows you to boost the signal for partial blockages. And this allows measurements to continue even with a slight contamination. The instrument's also mechanically designed to not trap any debris. There's no sharp corners or pockets where debris can accumulate, especially on the windows. Surprisingly, we don't even need to have a filter for this analyzer. We do provide a bug screen, which keeps large bugs from getting sucked into the system. And there's also a rain shield for those that want to avoid getting rain sucked into the analyzer. But filters, like those typically used, like the Gelman filters, aren't needed. And there's some benefits to not even having the filter. One of those is that you don't have the attenuation of H2O that sometimes happens when you get water vapor trapped in the filter. In addition, filters can create resistance to the flow. And if you have that resistance, then you're going to have a larger pressure drop, which again comes back to the point that you need a larger pump, which would require more power. So having this open system without a filter that doesn't contaminate easy is a real benefit. So other closed path analyzers can be difficult to open. You might require a set of tools to do that, and you most likely have to bring it into a laboratory in a clean environment to do that. We've done a lot of field testing here in Nebraska. We've been in So those of you that have been out here know that there's a lot of cornfields, and you can find a lot of dusty pollen air, and we haven't had any issues with that at all here. Okay, I hope that answered your question, Martin. Moving back into the presentation here, I just wanted to point out a few other details about the cell. The volume inside is a small volume. It's 16 cubic centimeters. There's fast temperature on the inlet and the outlet, and fast pressure in the center. And the optics, of course, have low sensitivity to contamination. Okay, now here is the Webb-Pierman-Leuning term, or the WPL term that I briefly touched on. This is the standard term that is applied to all eddy-covariance applications to correct for the fluctuations in the measured airstream due to dilution and thermal expansion and pressure expansions. The WPL term, established back in 1980 for open path analyzers, consists of two major terms. There's the latent heat flux portion, or the LE term, and the sensible heat flux portion, or the H term. There's also a pressure portion, known as the P term, and that's usually neglected. However, it could be important if you're measuring in a fluctuating pressure field, such as near mountaintops, or even on the edge of a building, for example. Now, in close path analyzers, the H term is usually considered negligible because of the severe tube attenuation of the temperatures inside the long intake tube. So only the LE term is applied to the frequency response corrected covariances. However, when you have these very long tubes, you start to lose some of the water vapor fluxes. And that's kind of what I was touching on earlier. And you can even lose some of the CO2 fluxes if you have very long tubes. With the 7200 here, and utilizing a standard 1 meter intake tube, the tube can attenuate about 95 to 99% of temperature fluctuations. That was found again by Clement in 1998. And it depends on things like the flow rate, the ambient H flux, surface roughness, thermostability, and instrument height, for example. So to apply the remaining 1 to 5% of the temperature fluctuations that still might occur, these can be measured with those fast temperature sensors inside the cell. And while in-cell H fluxes are probably negligible in most cases, you can still be on the safe side and utilize the H fluxes from the T in and T out and apply them in the WPL term if you'd like. Similarly, we have added the pressure sensor to help capture any ambient pressure changes if one would like to apply the P term that's usually neglected here. Many pumps used for eddy covariance are either diaphragm or rotary vane pumps. And now, especially with diaphragm pumps, the up and down motion of the diaphragm can create small pressure perturbations. So sometimes people will use a buffer volume before the pump, and that helps dampen some of those fluctuations, but that's not always the case. So here at LI-COR, we actually designed and developed a new flow module that we're going to be releasing with the 7200 that uses a blower. Now, this greatly reduces any pressure perturbations, and also as a beneficial feature, it operates at very low very low power requirements. And again, Bill's going to cover this flow module a little bit later in the webinar. Okay, this next graph here shows fast temperature data from the 7200 CO2 H2O analyzer. On the left-hand side, you can see the temperature in degrees C, and the data across here is collected in 10 hertz time. So what you can see in this graph here is that the effectiveness of the temperature sensors and the pressure sensors. In this particular graph, we're looking at daytime temperatures shown. What you can see is that it's a bit warmer inside the cell. This is due to the solar load, internal electronics, and we actually purposely do this to prevent condensation. So the instantaneous temperature fluctuations here are attenuated by about 95 to 99% on average. And this is really great to see because that helps with doing the H term corrections in the WPL term. And the remainder of these temperature fluctuations are captured by the sensors directly. Now, this is really awesome because, one, you have less corrections that you have to do in the WPL term, and two, you have direct measurements of these temperature fluctuations, and you can do these corrections. This second chart here shows fast pressure data collected from the 7200. Again, on the left-hand side, we show pressure in kilopascals. The data is collected in 10 Hertz scans. And what you can see here is that the flow rate through the cell is at 14 liters per minute. So fluctuations here are about 0.1 kilopascals if you're to not use any kind of a buffer volume. But if you are to use a buffer volume, fluctuations dropped down to 0.02 kilopascals. So that's really great to see. And these measurements were actually taken before we've developed our new flow module that uses a blower. So that will have even a bigger improvement once we are able to establish that. Now notice that the change in pressure is only 0.35 kilopascals. And what you typically see in a closed path system are pressure drops of about 40 to 50 kilopascals. So this is a huge improvement. Also notice that, again, we're not using any kind of filters here. So if you are to have any kind of pressure changes, and you need to apply these to the P term for expansion, as I mentioned earlier, the 7200 has the ability to measure these pressure fluctuations, and you can correct your data even further. So now we wanted to make some comparisons of the 7200 with the standard gas analyzers. This LI-7500, the open path analyzer, and the 7000 closed path analyzer. As many of you are familiar with, these are used in hundreds of Flux sites worldwide, have been used for several years now for making these measurements. What we're going to compare is the 7500, which is the open path standard for CO2 and H2O concentrations. We're going to compare the 7200 for the concentrations, the H2O flux, and also the frequency response for both CO2 and H2O. The 7000, which has been the standard for a closed path analyzer system, we're going to compare the 7200 for CO2 concentrations and CO2 fluxes. And all the data we're going to show in the next couple slides have been collected at 10 Hertz and processed using the FluxNet methodology that was established by Onboard back in 2000, which is hard to believe it's about 10 years ago now. So here in this graph, we're looking at absolute CO2 concentrations measured with both the 7500 open path and the new 7200 enclosed path analyzer. On the left-hand side, we have the CO2 in parts per million. Again, the data is collected in 10 Hertz. And this is data collected out in a ryegrass field here in Nebraska. And what we've done is actually zoomed in on the scaling so you can really see how close the two analyzers are. The data is really right on top of each other. The data here can be seen as almost always within 2 ppm, but most of the time it's within 1 ppm of the LI-7500 data. So the instantaneous 10 Hertz concentration values here resulted in mean concentrations being within a fraction of a percent from the standard 7500. This graph depicts hourly CO2 fluxes, FC, and hourly H2O fluxes, LE, over 3 days during an experiment in the Florida wetlands. So on the graph here, we show the CO2 flux, or FC, is on the left-hand side. The H2O flux, or LE, is on the right-hand side. Now the top red line is for the CO2 fluxes, and that's collected by the LI-7000. The green circles are from the 7200 and correspond to the left axis as well. You can see that they lay right on top of each other. The bottom dashed magenta line is for H2O fluxes, or LE, measured with the LI-7500. The blue triangles represent H2O data collected with the LI-7200. Again, you see the water fluxes correspond to the right-hand axis, and all the data points are right on top of each other. Okay, this next graph is what's known as the frequency response chart, showing what kind of data loss is happening at different speeds of data collection. And what you can see here is that the frequency loss of the 7200 data is really quite small. It's a little bit higher than that of the 7500. On the left-hand side, you can see the CO2 fluxes and in the right-hand graph you have the H2O fluxes. And both of these are used to compare against the LI-7200. Now, frequency losses that are shown with the LI-7200 are mainly attributed to sensor separation, for example, the distance between the analyzer and the sonic, and path averaging. Now, with the new 7200, the frequency losses are attributed more to tube lengths, but also to path averaging, which is the same as the 7500. So on average here, the 7200, for example, with a half-meter intake tube, will have 12% frequency loss versus 8% typical loss with the 7500. Now, if you move to a longer 1-meter intake tube, the 7200 has a 13% frequency loss versus a 9% frequency loss for the 7500. So these results are very good and encouraging. They're as we expected, and the high frequency attenuation occurs with the slightly longer intake tube. Now, for a comparison, the frequency loss for a closed path analyzer with the 4.5-meter intake tube can be anywhere between 15 and 30% frequency loss. And this last graph that I wanted to show with some data from the field experiments are hourly CO2 and H2O fluxes. And what you can see here is that they're within 2.5% of the standards for the LI-7000 and the LI-7500 respectively. All these experiments had the appropriate corrections applied, and what we observed is a 2.5% difference, as I mentioned, but it's not statistically significant. The p-value is less than 0.05. And what I also wanted to point out is the data has been occurring since over 3 years now. We've been collecting data, field testing this, beginning back in May of 2006. And this includes 3 years worth of data here. And you can see an excellent relationship between the two analyzers. So now I'd like to turn things back over to Bill. He's going to talk a little bit about configuration. And Bill, back to you.
All right, thanks, Dave. And hello again, everybody. As Dave mentioned, I'll go ahead now and talk through some of the configuration issues and give a little bit more detail about the different components of the LI-7200 system. To begin with, just to reiterate, the LI-7200 analyzer was designed for use in remote field environments. Something that's very different about the LI-COR gas analyzers is the way we build them and design them to be put out in the middle of nowhere, wherever the interesting scientific data needs to be collected. We want to have instruments that you can take there, and the LI-7200 is another one in that line that we've designed, and we expect it to be used in some exotic environments and situations. Also, the LI-7200 can be mounted on top of the tower at the sampling point of the measurements, and that's an important difference as well, as Dave was talking about, related to long tubing lengths with traditional closed path analyzers and the kind of attenuation and tubing delays and issues that you find there. Being able to put the instrument on top of the tower is really an important change that comes with the LI-7200. The next thing that we think is really unique about the LI-7200 is that it's easy to open and clean without the need for tools. Dave mentioned this earlier, and it's something that really makes the instrument much more usable in the field.
Bill, I'm going to jump in here really quick. I have a question here about your first point, and Jose is asking, do I need a climate-controlled instrument enclosure to house the LI-7200?
Okay, thanks, Ashley. That's a really good question, Jose, and I should have been more clear about that probably earlier. No, in fact, you do not need to put the LI-7200 in an instrument enclosure. Much like the 7500, the instrument is weatherproofed, and it's designed to be put up on the tower arm at the top next to the sonic, and you don't need to try to enclose it in anything. It's designed to operate over a wide temperature range, minus 25 C to plus 50 C, so you don't need to try to give it a temperature-controlled environment or anything like that. So when we say you can put the analyzer at the top of the tower and have a short intake tube, that's true, and you don't have to worry about enclosing it at the top of the tower because it was designed to be placed there without an enclosure. So thanks for asking that. It's good to clarify and make sure that's clear to people. You're not going to need to try to elevate your enclosure because now you don't need an enclosure for the 7200. As I was mentioning just a moment ago, the instrument was really designed for easy cleanability in the field, and the image here shows you an LI-7200 with the optics opened up for cleaning. Dave talked about this a little bit earlier, but all you do is unscrew the 2 screws at the top of the instrument and pull the top open. Then you can remove the optical cell, and that's the piece on the right there. So then you can just take a cloth or the shirt tail off your shirt and wipe off the windows. You can run a swab down through the tube and reassemble the instrument, push it back together and screw it closed, and that's all there is to cleaning the instrument. And again, having put instruments in the field for a long time here at LI-COR and having people on staff who've been out in the field trying to keep things running for years, we appreciate how hard it can be sometimes with a closed path analyzer to keep the optics clean. And that's why we designed the 7200 to be so easy to use and so easy to clean in the field. It's got a straight path for the optics, so there's no bouncing, there's no mirrors. A lot of these newer laser-based instruments are going to have mirrors in them and high reflectivity cavities, and cleaning those can be extremely difficult, and keeping the reflectivity high enough to get good measurements. So having an instrument like this that you can just pull your shirt out, wipe it off, and put it back together, we think is going to make using the instrument in the field a lot easier. Now we're going to go ahead and talk about some of the components of the LI-7200 system. The first piece we'll discuss is the LI-7550 Analyzer Interface Unit. That's the what you may have thought of as the white box with the 7500 instrument. This is an updated version, and it's used for both controlling or housing the high-speed electronics and also providing for inputs and outputs. Similar to a 7500, we have SDM outputs if you're synchronizing with a Campbell data logger. We have RS-232 outputs. We've got digital to analog outputs, and now we've got more of those. We have 6 now. And also now something new with the LI-7550 is an Ethernet output. So you can attach it directly to a network or to a computer for logging. That Ethernet connectivity is a significant step forward because now you can, if your site is networked, you can remotely access the instrument, monitor its performance, and even retrieve data from the instrument via the network without having to visit the site. So that's another step ahead when you've got remote field sites and instruments positioned all over the world. Now you can access them very quickly, make sure they're performing properly, collect your data, and move on without having to spend a day going out to the field site. Something else that's significant about the 7550 now is that it's got additional analog inputs, and we designed it so that you can now integrate your sonic anemometer directly with the gas analyzer. So now if you are making flux measurements, you can take the analog outputs from any typical sonic, whether it be from Campbell Scientific or Gill or METEC, RM Young, any of the common sonic anemometers with analog outputs can be brought into your 7200, and we can time synchronize the data collected so you can get your U, V, W, sonic temperature, CO2, water vapor, diagnostics, all time stamped and synchronized together. So that's another nice feature of this new instrument is just being able to get that data put together quickly and easily. The LI-7550 also has onboard data logging, and you'll see in this image on the right here there's a USB stick that you can insert for data collection. So now not only can you integrate CO2, water vapor, and sonic data, but you can log it right on board your gas analyzer now. It's a high-speed logging, and it does get everything synchronized up for you. So again, we're just trying to find ways to make it easier for people to make the measurements they need, allow people to make the measurements with the least amount of power and the easiest setup. So these are some things that we think are significant about the 7550 component of the instrument. Something else that's really nice is that everything is set up with a Windows interface. So everything is point and click. It's very easy to get the instrument set up, check zeros and spans. When you want to get your auxiliary inputs put together, there's no difficult programming or anything that you need to deal with. You can just go ahead, point and click, enter in your coefficients, tell it how often you want to log data, and get things started, and then you're set. So it's been made very easy to use. Okay, before we go any farther, we've got another poll question for you. I'm in marketing, so I like polls. This time we're going to ask a little bit about the the way that you would like to collect data from your sites. And now that you've seen the LI-7500, you know that it can log data on board, and you know the different ways that it can output data. We'd like to know what method of data collection you'd prefer to use at your sites. So would you prefer to collect data over the Ethernet, either on a network or to a local computer? Would you rather send out analog signals for a data recorder? Use SDM to connect to a Campbell Scientific data logger? Or just log everything right there on the removable USB storage for the 7550. So please go ahead and enter in your answers here, and in just a moment we'll continue on.
All right, it looks like we've got the poll working this time, so if you could go ahead and answer via the quick poll option instead of your questions function, that would be great. Thank you.
Okay, thanks a lot, everybody. It's always fun to see the data come in and see what people are thinking, and this will be very helpful for us as we continue to move forward and look at ways that we can help people get systems integrated and get data output more easily. It's important for us to know what you'd like to do so we can help provide instruments that are functional for you. The next component of the system that we're going to talk about is the flow module. It's called the 7200-101 flow module, and it is an optional accessory for the 7200 system. If you've already got a pump or a flow system designed for your flux towers, you can use those and interface them with the 7200. It's very flexible. But if you don't already have a solution and you're looking for something that can be fully integrated and be a very low power consumption solution, we did design the LI-7200-101 flow module just for that. And what that is a precisely controlled flow. The user can select the flow rate that you want, again through the Windows interface, and then there's active flow control. So the module is going to monitor flow consistently, and if there's fouling in the filters or if anything is happening, it will automatically feedback and make sure that it maintains the flow rate that you've asked for. It interfaces directly with the LI-7550. So again, the interface with the flow module is through the Windows application, and then it will also output data. So it outputs the flow rates, it outputs your diagnostic information, and everything else that you need straight into your data set with your LI-7200. So there's full integration with the system, and it just makes it very easy to use. The reason that we designed this was because, again, it's not very helpful to have a low power consumption gas analyzer and then have to plug in the pump. That's not going to get you where you need to be for remote field sites. So we really took it upon ourselves to design something that would allow for this enclosed analyzer to operate on solar panels. And that was a really key driver for this product and this project, was how can we help people get maximum data collection at remote sites without needing power. And that's where this flow module comes into play. Again, it's very easy to interface with, and it provides 15 liters of flow, which is optimal for eddy covariance measurements with this analyzer. And it can provide those 15 liters of flow for 15 watts of power nominally. Speaking of power, next we want to talk about the overall system power consumption and the fact that typically these analyzers can be operated in the field with solar panels, so you won't need to install mainline AC power. This next picture is from a field site in the Florida Everglades, and the tower there in the back is actually operating an LI-7200 with a flow module. It's also got an LI-7500 CO2 analyzer that we were using for comparison data, and it's got our new LI-7700 methane analyzer. All of these instruments and the sonic anemometer, the ancillary meteorological instruments that you see there, and the data logger are being powered off those solar panels in the image and the battery pack there. So again, we just think it's really significant that the LI-7200, along with the flow module, can provide you with the measurements that you need and only require about 27 watts of power. So this is, again, something that we think is a significant step forward in being able to get the measurement made where you need to make it instead of where the infrastructure allows you to make it. Okay, here's our last poll question for the day, and now we're going to ask you a little bit more about the infrastructure that you require at the field sites that you've got. And when you're getting ready to instrument a new tower in a new location, we'd like to know about what kind of constraints you have to consider when you're getting that tower set up. And we'd like to know, if you were to install a new Flux tower somewhere, would you operate it with mainline power, or would you prefer to operate it with solar and battery power? So thinking about new sites, would it be easier to just install AC power at the site? Or do you already have AC power at the site? Or would you go ahead and want to operate with a solar power and battery power system? So again, we'll just take a moment and let everybody get their answers in, and then we'll move forward and wrap up the discussion today. Okay, just to summarize and wrap things up here for the day, we'll go ahead and just recap some of the advantages that the LI-7200 has that are similar to open path analyzers. One, there's small, easily correctable flux attenuation loss because there's a short intake tube. There's very infrequent calibration requirements because the instrument is very stable over time. There's minimum maintenance requirements. The optics are such that they don't require a lot of attention, and once you get things deployed, they pretty well maintain themselves. The instrument has very low power requirements, so the infrastructure at the site can be minimal. And the small size and lightweight and weatherproof design make it really just easy to use out in the field. The instrument also has a lot of advantages related to closed path analyzers. Some of the key ones are minimal data loss during precipitation events or icing or condensation. It's really easy to verify zero and spans automatically. You can plumb in a tank at the site and periodically run through a zero or a span gas, make sure the instrument isn't drifting more than you'd like. And it's got a very stable optical cell temperature, which really, again, decreases drift and noise in the signal and gives you a very good signal. So that's all we had to present today, and now we can go ahead and respond to some more questions and answers. I think Ashley's been reviewing those throughout the discussion, and she might have a few that would be interesting to the entire group. So, Ashley, were there any other questions that we can answer before we quit today?
Yeah, thanks, Bill. We've got several questions coming in here, and the first one I picked out was from Herbert, and he says, why call it enclosed?
Okay, Herbert, that's a good question. It's not just marketing talk. What we wanted to do was help explain to people that this analyzer is different from a traditional closed path instrument. And being able to collect data during precipitation and condensation events and not have the data dropouts from open path is really important. And so we want to have an enclosed optic that allows for that. But at the same time, traditional closed path analyzers are going to require typically mainline power. They're going to require temperature controlled enclosures and other infrastructure that the LI-7200 doesn't. They're going to need long intake tubes that are going to attenuate your water vapor fluxes. And so the 7200 is really a new kind of instrument that takes an open path analyzer and encloses it to give us what we feel is really the best opportunity to make remote flux measurements. And that's why we've kind of branded this an enclosed analyzer, because it's not a traditional open path and it's not a traditional closed path. It's really something new and different.
Great. I've got another question here, this one from Yang. What are the key differences between the 7200 and other closed path analyzers?
Actually, Yang, that's a good question. And as I was just kind of mentioning, I think I was just speaking to Herbert about a few of the key differences. But Mainly, you're going to see that the 7200 has the low power consumption that you need for remote field deployment. It's weatherproof, so it can be put at the top of the tower, and you're not going to have to provide air conditioning or heating to keep the instrument working properly. It's really resistant to contamination, and the optics are very robust. So with traditional closed path analyzers, once you start to see some accumulation of debris, your signal drops off really quickly, and so you're required to have some pretty tight particle filters, usually on your inlets. As Dave talked about earlier, those particle filters are going to attenuate potentially some water vapor fluxes, and they're definitely going to increase pressure drop for the system, which means more power. So that's another key difference with the instrument. And I think something that's really new and exciting about the 7200 that's different from any other analyzers on the market are that now we can integrate sonic anemometer data, and we have onboard data collection. So now, really, with the LI-7200, we provide a complete solution for fast eddy covariance measurements. You can input your sonic data. You can collect that right alongside the 10 or 20 hertz data that you're collecting from your CO2 and water vapor analyzers. You can log that all there with a timestamp. And we've got software also that makes it easy to get that data formatted so that you can drop it into your Flux calculators, such as eddy-RE or other calculators like that. And it just makes for a very seamless transition from density values of CO2 to calculated fluxes.
Thanks, Bill. I've got one more question here, but before I ask it, I just want to remind the participants that they can keep asking questions. Our panelists will stick around and answer them via our Q&A function if since they weren't actually asked live over the line here. The last question is from Katerina, and she asks, "Can't I just put a cowl shroud on my 7500?"
Yeah, Bill, let me take that one. That's a good question, Katerina, but there's a couple issues that could arise from doing something like that. The first one I can think of off the top of my head is if you have this shroud inside the 7500 and you have a pump and a small tubing and you're pulling the gas stream through your 7500, you're going to create a negative pressure up there, and what can happen is potentially you're going to be pulling outside air in through around the gaskets of the shroud and kind of contaminate your sample in that way. Some people have thought about, what if I can permanently seal the shroud in there? Well, then you have some issues with if you have different materials. For example, the shroud is made of a PVC and a different kind of metal than the rest of the head. And during hot and cold temperatures, things will expand and contract at different rates, and you could cause some physical stress to the head. With the 7200 now, you can have the fast temperature and pressure, the benefits of that. So you can use the WPL term, which you wouldn't have with just putting the shroud in there. And I guess finally, if you were to somehow get some contamination or the inside got dirty, and you have a permanently sealed head, then how are you going to open it and get that clean? So you'll run into some troubles there. So I hope that answered your question, Katerina.
Thanks, Bill and Dave, for the informative presentation. And thanks to our audience for joining us today. It's clear to me after listening to the webinar that the LI-7200 is designed for making high-precision CO2 and H2O measurements utilizing minimal power while maintaining high long-term stability at virtually any field site around the world.